Today, the goal is going to be using matrices as we've worked through them to solve systems of equations. Now, in the past, you've solved systems of equations using either elimination or substitution. Matrices offer another way of going about solving them. Ultimately, I'm pretty confident that you're going to prefer using matrices to solve systems rather than the algebraic methods that we've used in the past. Now, definitions that we need to get. First, we're going to have what's called a coefficient matrix. Coefficient matrix, we're going to take the coefficients from our system and we're going to enter them into a matrix. Now, the coefficient matrix has rows and columns containing coefficients from the system of equations. The first row is going to be the first equation. The second row is going to be the second equation. The first column is going to be the first set of coefficients. The second column will be the second set of coefficients. So for our system of equations here, 5x minus 2y equals negative 6, negative x plus 5y equals 15. Our coefficient matrix is going to be the 2 by 2 matrix, 5, negative 2, negative 1, 5. Now, we can actually take our system of equations and decompose it into different parts. We've got our coefficient matrix, which comes out of the coefficients. Next, we have what we call our variable matrix. Variable matrix is the set of variables that we're solving for. In our case, x, y. It's just the n by 1 matrix containing the variables, n being however many variables there are. Here it is a 2 by 1 matrix because we have two variables for which we're solving. If we had a 3 variable system, it would be a 3 by 1 matrix with x, y, z. If we had a 4 variable system, we would have w, x, y, z, and so forth. And lastly, we have what's going to be known as our solution matrix. Again, an n by 1 matrix containing the solutions. For us, that was negative 6, 15. Putting this all together, when we had 5x minus 2y equals negative 6, negative x plus 5y equals 15, if we take our coefficient matrix, our variable matrix, and our solution matrix, that actually gets us a matrix equation, where we've got our coefficient matrix multiplied by our variable matrix will equal our solution matrix. Checking this by multiplication, seeing that this is exactly what we've done so far. Now here's where the right-hand multiplication, we are multiplying by the variables on the right side of our matrix. If we multiply this, we'll see that it is in fact the system. Taking our rows by columns, well, we have a 2 by 2 and a 2 by 1. The inner dimensions match. And it should give us a 2 by 1 matrix. So rows by columns, we're going to have 5 times x plus negative 2 times y. We're going to have negative x plus 5y. If we do the multiplication, and that equals our solution matrix. And as we know from past experiences, two matrices are equal whenever we have same dimensions, 2 by 1, and as well as the corresponding elements match, which connects back to our initial system. Now what we're going to actually do as a means of solving this, we're going to stitch together, we're going to combine our coefficient matrix with our solution matrix into what we call an augmented coefficient matrix. Our augmented coefficient matrix, we're going to combine the coefficient and solution matrices. So we have 5, negative 2, negative 1, 5 was our coefficient matrix from before. And I'm going to combine that. I use a dashed line to indicate that I'm really putting these two together, stitching these two together with my solution matrix. Negative 6, 15. Creating the coefficients combined with the solutions. I call this my augmented coefficient matrix. Now we're going to take this and we're going to manipulate this in ways to solve the system for us. Now we're going to be using 3 what we call row operations. The idea behind here is we can take our matrix and we can manipulate 1 row or 2 rows or however many rows at a time, ultimately leading towards a solution. I'll get to that in a moment. Now the row operations that we are allowed to use, we can swap 2 rows, just exchange them, switch, take the top one, switch it for the second, take that, put it back to the first. We can multiply one row by a scalar factor. I can multiply the entire row by 2. Does not change value. That's equivalent to multiplying an equation by some value, trying to get those common opposite coefficients. And the third operation that we can replace a row by adding another row. We can combine two rows to make a new row. The ultimate goal here is we're going to take our augmented coefficient matrix and we're going to turn this into a reduced row echelon form. Something that looks like this, where we have ones on the diagonal, zeros everywhere else. By doing so, by combining our rows, this is going to create something. Now, if we think back to our coefficient variable matrix, we would have x equal to a, y equal to b when we follow through with the multiplication. This here is known as the identity matrix. Identity because we've got ones on the diagonal, zeros everywhere else. If we can take our augmented coefficient matrix for our system of equations and turn it into the row reduced echelon form, then whatever those values are, those are the solutions for x and y. Just a notation, notice on the wording that we have, reduced, we're reducing everything to ones and zeros. This row echelon form, echelon is a set of staircases. So you notice that they're going to be ones on a diagonal. So reduced row echelon form is ones on a diagonal, zeros everywhere else. All right, I'm going to go back to our initial system of equations. This is the first problem on the practice worksheet that I'm asking you to do. With our system of equations in our augmented coefficient matrix, our row operations, we can exchange anything. Now here, I don't see any need to exchange anything, and I'll try and show one of those later on. But what I'm going to do is I'm going to change these to make them easier to add together. I'm trying to turn this into a 1, this into a 0, this into a 0, this into a 1. First thing I'm going to do is I'm going to take row 2 and I'm going to multiply by 5. I'm going to notate that by doing 5 times row 2. I'm going to indicate R2. This gives us a new matrix. Did not change the first row, so I still have 5, -2, -6. But now my second row becomes -5, 25, and 5 times 15 gets us 75. So I multiplied the second row by 5. 5 times row 2 gets us that. Now the reason is I have these values are opposite. My next move, I'm going to take row 2 and I'm going to replace it by adding row 1. Row 1 does not change, so that's going to stay 5, -2, -6, but row 2 is going to add row 1. So -5 plus 5 gets us a 0, which is what we wanted. 25 plus -2 gets us 23, and 75 plus -6 when we add row 1 gets us 69. I'm going to step in the right direction because now I have a 0 in that place. I'm going to keep on working row 2. We have a 0, we want a 1. Well, here's where we can multiply the row by a scale factor. I'm going to take row 2, I'm going to leave row 1 alone, but I'm going to take row 2 and I'm going to multiply it by 1 over 23, or divide by 23. Dividing by 23, 0 divided by 23, still 0. 23 divided by 23 gives us 1, giving us that set that we wanted, and 69 divided by 23 gives us 3. So we're in the right direction, where we've got this value that we want. I need this to become a 1, this to become a 0 now. I'm going to use this 1 to get rid of this 2. I'm going to change row 1 by taking row 1, and I'm going to add 2 times row 2. So I see that I have -2 there. I can multiply this row by 2 and add it. Now row 2 stays the same. Row 1, I'm going to 5 plus 2 times row 2, 5 times 0 stays 5. negative 2 plus 2 times 1, negative 2 plus 2 gives us 0. And negative 6 plus 2 times 3, well, 2 times 3 is 6, plus negative 6 gives us 0. We've eliminated that element. We have zeros everywhere except for the diagonal. We need to make this a 1. So one more step. I'm going to multiply the top row by 1/5. So 1/5 times row 1. That's going to give us 1, 0, 0. Second row is 0, 1, 3. And we've turned this into our identity matrix followed by our solution set. This tells us now that x equals 0, because that's the first value, the first column, and we have y equals 3, because y equals 3. We have a different way of solving our system. This is using row operations in an augmented coefficient matrix. That was example number 1 off of the practice. I'm going to try a different one, something that's a little bit more complicated. Not that that was simple. I'm going to try one that's a little bit more with 3 variables. I have here set up the augmented coefficient matrix that's given in exercise number 8. I'm going to say ignore the directions on the worksheet. This would be our augmented coefficient matrix that's provided, comes from this system of equations. Now our goal is to rewrite this so we have 1s on the diagonal, 0s everywhere else. That's going to solve for x, for y, for z. Steps I'm going to take here, I notice that there's already a 1 and a 0 in this row 2. I want that 1 to be in the very first position. So here's an example of the row operations where I'm allowed to exchange 2 rows. I'm going to take row 1 and swap it with row 2. Row 3 stays the same. So row 1 becomes 1, 0, 4, 0. Row 2 becomes negative 5, negative 4, 3, negative 8. And row 3 stays as it is. Now I've got that 1 in that first position. I'm going to use that to get rid of the negative 5. I'm going to use that to get rid of the 3. What can I do to get rid of the negative 5? I'm going to take row 2, and I'm going to add 5 times row 1. I'm going to bring that down to the next line. Row 1 is going to stay the same. So we have 1, 0, 4, 10. I'm going to take row 2. Because of that negative 5, I want that to be a 0. Take negative 5 plus 5 times 1 gets us 0. Negative 4 plus 5 times 0 keeps that negative 4. 3 plus 5 times 4, that's 23. And negative 8 plus 5 times 0 keeps it negative 8. Now I also can get rid of that 3 element in row 3 at the same time. I'm going to take row 3, since I'm already done with row 1, already done with row 2, I'm going to take row 3 and I'm going to subtract 3 times row 1. So I have 3 and I'm going to subtract 3 times 1. 3 minus 3 gets us 0. I have that 1 in the key position, 0 is underneath it. Negative 5 minus 3 times 0 stays negative 5. 5 subtract 3 times 4. Well, 3 times 4 is 12. 5 subtract 12 gets us negative 7. And lastly, negative 10 subtract 3 times 0. Negative 10 keeps us negative 10. So you can see that I can take 2 operations at the same time. I've got the 1 in the key spot, 0's underneath. There's a 0. We need to make the negative 4. We need to turn that into positive 1. We need to make this a 0. Now, I notice that between the two of these, I'm going to start working things out. I'm going to multiply row 2 by 5. I'm going to multiply row 3 by negative 4. So row 2 is going to be multiplied by 5. Row 3 is going to be multiplied by negative 4. Thinking ahead, that's going to give us negative 20, positive 20. Just like with elimination, that's going to work itself out. This gives us now, row 1 stays the same. That's a 10. That's a 0. Oops. 0. That's a 0 all the way back there. All right, we have 0. 5 times negative 4 gets us negative 20. 5 times 23 gives us 115. 5 times negative 8 gets us negative 40. Negative 4 times 0. Negative 4 times negative 5. Negative 4 times negative 7. That's 28. And negative 4 times negative 10 gives us positive 40. Make that a little bit better. Nice thing here is that those values I can add and cancel. I need a 0 in this row 3 spot. So I'm going to take row 3, I'm going to add row 2. Row 1 stays the same, 0 this time. Row 2 stays the same. And row 3, well, I've got 20 plus negative 20, gives us a 0. 28 plus 115 gives us 143. It's not that bad. 40 plus negative 40 gives us 0. We've got a 1, 0, 0, 0, negative 20. We're going to get rid of that in a moment. 0. Now this 143 needs to be a 1, because 1's on a diagonal, 0 is everywhere else. Notice, that's going to work out all right. I'm going to divide or multiply by 1 over 143 to row 3. Everything stays the same except for row 3. Gives us 0, 0, dividing by 143, 1, 0. So I started off, I got a 1 in the first spot. I used that 1 to get zeros underneath. So now whenever I combine anything, nothing is going to put a value into the first column. I then combined to eliminate a value in the second column. So I had zeros above and below the second column. And now that I've got the 1, I'm going to work backwards. I'm going to use this 1 to eliminate that 115. I'm going to use this 1 to eliminate that 4. Works out nicely here because that 1 is worth 0. But I need to eliminate the 4. I need to make this a 0. So I'm going to do row 1, and I'm going to subtract 4 times row 3. That 1 is a nice piece to use. I'm going to use row 2, and I'm going to subtract 115 times row 3. Not as bad as it looks because it's just 115 times 1, and it's designed specifically to make that 0, to make that 0. Let's do that work. Row 1, subtract 4 times row 3. It's going to be 1 subtract 0. 1. 0 subtract 0. 4 subtract 4, giving us 0. And 0 subtract 0, keeping that 0. Row 2, we have 0 subtract 0. Negative 20 subtract 0. 115 subtract 115, 0. Negative 40 subtract 0, negative 40. And a third row stays the same. One last step. I need 1s on a diagonal. We need to convert that negative 20 to a 1. So I'm going to multiply row 2 by negative 1 over 20, or divide by 1 by 20. 1, 0, 0, 0, 0. Negative 20 divided by negative 20, 1, 0. Negative 40 divided by negative 20, 2, 0, 0, 1, 0. We've turned this into the 3 by 3 identity matrix, augmented with our solution set. First column is x, second column is y, third column is z. We have x equals 0, y equals 2, z equals 0. We have solved the 3 by 3 system using an augmented coefficient matrix. And you can check to see that that does in fact work back to the initial values. So that's what we've got. Try out the practice. Good luck. We'll go from there.